Okay, testing. 1, 2, 3. Perfect. Okay, good morning, future presidents. Last time we had just started on the greenhouse effect. We had been talking about thermal radiation, so we're going to finish up our discussions about that today. There are a couple of demos that weren't available last lecture, so let's start off with those. Remember last time we said that we were talking about the electromagnetic spectrum, and remember visible is a very small fraction of the overall electromagnetic spectrum. It only goes from 400 nanometers up to 700 nanometers. And so there's a huge range of electromagnetic spectrum that is not visible to the human eye. And the one that we were really focused on, or one we talked about most, was the infrared. And the reason is because at temperatures in the Earth around us and typical temperatures around us, everything is glowing at infrared wavelengths. So somewhere around 10 microns or 10,000 nanometers, depending on your whether you like microns or nanometers. Let's see. So I've got a couple demos here of infrared radiation. So let's see. Wei, can you swap to the first screen? Great. Okay, so what I've got here is just it looks like a normal camera. I could do a little Blair Witch trial demo here if we wanted. So this camera is, let's see what we can pick up here. There we go. There's the audience. Nice. Wave to the camera. Okay, so this is actually a very special camera because it picks up at both optical and infrared wavelengths, but you cannot see the infrared right now. Okay, we're going to turn on this very special flashlight, which looks very unimpressive, but this is glowing in infrared light. Okay, so you can't see it right now, but we'll be able to pick it up through this camera. So let's see. Wait, I actually need you to turn off the lights in 1 second. Let's let this last person get a seat. No rush. Okay, great. Let's go ahead and turn off the lights. So I think we're definitely going to need the front lights off on me. Okay, there we go. So spooky, okay? This is a good Halloween demo, huh? Let's see if I can turn this on. Ooh, there we go. Okay, so if I can line this up straight, you can start to see the flashlight a little bit there in the infrared. Let me see if I can do my face, make it a little bit more dramatic. Let's see, is that even coming through? There we go. Yeah, that's a good look, isn't it? I like that. So you can see this is completely invisible to us, to the normal eye. So, but in the infrared, this is moderately bright. This isn't exactly the brightest thing. This flashlight is in the near infrared, so this is pretty close to visible wavelengths. So let's switch over. Actually, just keep it on their way. So let me switch the cameras. I'm going to switch over to the other camera up here, which is actually in the far infrared. So this camera is designed to pick up wavelengths that are closer to human body temperatures. So you can obviously imagine the military applications of a camera like this. But there are lots of scientific applications for this as well as engineering applications. So let me pan around the audience here. And you can see what I've been telling you all along is true. You guys are all brilliant light bulbs glowing. Let's see, we got some nice waves up here. So there we go. Yep, that is you. That is you in the infrared, emitting your 100 watts. So, if you fall asleep and fall down on your chair, I'll be able to find you. So, stay awake. Okay, you can also see, so this little scale on the right there is the temperature in Celsius. So remember, the hotter you are, or the hotter an object is, the shorter wavelengths it glows in, and also the brighter it glows. And you can see how much hotter that you are than your environment. You can see this camera very clearly picks out all the people in the room, and all the chairs and the walls and stuff are actually very cold compared to the people. So that's why these cameras work really well. Okay, so let's turn the lights back on. And we can swap back to the normal camera. Okay, that camera is picking up at about 10 microns, which is the far infrared. Okay. That's about human temperatures. That's also the temperature of the Earth around us primarily, or close to around there. I mean, that's the radiation, the dominant wavelengths of radiation in the world around us. Okay, so let's use some of our knowledge of infrared radiation and talk about the greenhouse effect. So last time we went over what were the dominant 4 factors that go into the greenhouse effect, and let's just review those real fast. So the first is that, remember, we talked about how the Earth warms up. The Earth warms by absorbing sunlight. Okay, the sun emits primarily invisible part of the spectrum. Okay, it does have some infrared and some ultraviolet, but the primary energy output is in the visible spectrum. And the atmosphere is largely transparent to the visible. That's why we can see the sun and we can see stars. So most of that visible light actually comes through the atmosphere. Okay? And then when it gets reflected, it gets absorbed onto the Earth, it heats up the Earth, okay, and warms up the Earth. Okay? If the Earth were not cooling through some means, then it would just get hotter and hotter and hotter. Okay? So it has to have a means of cooling, and that primary means is radiation. Okay? That's because space is mostly a vacuum, so there's not a lot of conduction of heat away from the Earth or convection. Okay? It's primarily through the Earth's infrared radiation. Okay? And we'll see some numbers for that today, but that's primarily coming out in the infrared band, so especially the far infrared band around 10 microns. Okay? The Earth, the atmosphere. So if the atmosphere were completely transparent to both visible light and to infrared light, then the heat would come in, the light from the sun would come in, heat up the Earth, and the Earth would radiate out to space, and the atmosphere would actually stay relatively cold. So there'd probably be conduction from the Earth that would heat it up some, but it would not be as much as it is today. The atmosphere primarily heats by absorbing that thermal radiation. Okay? That's because the atmosphere is transparent to visible light, so we can see through the atmosphere with our eyes, but it is in large part opaque to infrared radiation. So infrared radiation gets absorbed. Okay, not completely, which we'll see in our models today, but partially. But that absorption of infrared radiation from the Earth heats up the atmosphere, and specifically the reason that the atmosphere is not invisible to infrared radiation is because of greenhouse gases. So greenhouse gases are largely natural gases. It's largely water, but there are other ones as well, which absorb infrared radiation. So these are the reasons, this is the primary reason the atmosphere heats up, or the primary means that it heats up. Okay, and the fourth part, I think is pretty obvious. If the atmosphere gets warmer, the Earth's going to get warmer. Okay? It's like you're putting on an electric blanket on the Earth. So it's obviously if we heat up the atmosphere, it's going to heat up the Earth as well. Okay, so let's make, my notes are around somewhere. Let's make a little model of the atmosphere. There we go. Actually, let's make a few models of the atmosphere and just try to understand some of these basics in terms of how the atmosphere itself and the greenhouse gases affect the temperature of the Earth. Okay? So to do that, we're going to start off with, well, we're actually going to look at two extreme cases, and we're going to see the Earth is really somewhere in between that. And the two cases we're going to look at are the cases where the atmosphere is completely invisible to infrared radiation, and the case where it is completely opaque to infrared radiation. So it either lets it pass unimpeded or it absorbs it completely. And those give the sort of the two extremes of what the temperature of the Earth could be. So let's do the extreme case number one. Okay, so this is the case of what the temperature of the Earth would be if we had no atmosphere whatsoever. So if we have no atmosphere, then there's nothing there to absorb the infrared radiation. So in this case, the Earth would heat up by absorbing sunlight, and then it would cool off by emitting its thermal radiation, and there would be no atmosphere to affect what that final temperature of the Earth is. So let's look at some of these numbers. So here is the sun shining down on the Earth. Okay. Let's see. Let's draw the Earth down here. Here is the surface of the Earth. Okay. And in this picture, we don't have any atmosphere above that surface. So it's just the sunlight's hitting the Earth, and that is the picture we've got. I'm going to move this up just a little bit. I know that wave machine is in people's way over there. So there is our diagram of the sun shining on the Earth. Okay. So the sun has an average amount of power per square meter. We talked about this a little bit when we talked a little bit about solar power, but it's 342 watts per meter squared. Okay. That is just the average amount of power in visible light that is incident on to the surface of the Earth in sunlight. So that's primarily in the visible band. Okay. So that amount of radiation power is in theory could go into heating up the Earth. Okay. The first effect that we have to worry about is the fact that well, you know this if you're out in space, not that any of you have been out in space, but if you are out in space, we can see the Earth, right? We can see the Earth because it reflects some of the sunlight that is incident on it. If it absorbed all that sunlight completely, then it would be, we wouldn't be able to see it in the visible wave bands. So the fact is the Earth actually reflects a fairly significant amount of the light that's incident on it, and that is actually an important factor. It reflects about 106 watts per meter squared. So that's just reflected sunlight. And that is 31% of the overall sunlight. This factor is called the albedo. And it turns out to be a really important factor. We'll come back and talk about that. So albedo is the fraction of the incident sunlight that gets reflected back to space. Okay. For the average of the Earth, it's about 31%. Okay. That, of course, varies depending on what you're looking at. So water and ice are much more reflective than, say, sand or farmland. Okay. But this is the current average for the Earth. It's about 31%. Okay. So that means when we take that off, so that amount of sunlight is just going reflected back. It's not going into warming the Earth. So that means the net amount of power that is coming into the Earth from sunlight is about 236 watts per square meter that is absorbed. Okay, so that is the power that is going to heating up the surface of the Earth on average. So remember, a watt, 100 watts is the bright light bulb, so this is about 2 bright light bulbs per square meter, okay, of area. That is about the amount of power that's going into heating up the Earth. Okay, so like we said in this point over here, that if that amount of power just came in and the Earth weren't cooling by any other means, then the temperature would just keep heating up. It would just get hotter and hotter and hotter, absorbing all that thermal energy. Okay, so, but the Earth does cool, and it cools by emitting thermal radiation back to space. Okay, and that thermal radiation is, let's say that's thermal radiation back to space. Okay. That thermal radiation we know comes from the Stefan-Boltzmann law. It's just their constant times the temperature of the Earth to the fourth power. Okay. And we'll see that that is emitted primarily in the infrared band. So that depends on what temperature that is, but the temperature that it comes out to be puts it pretty squarely right in the infrared band. So the Earth heats by absorbing the sunlight, and it cools by emitting this thermal radiation. Okay. So now, remember that this is a power per unit area, okay? Just like this absorption is power per unit area. Okay, so now, on average, the Earth is in equilibrium. Okay, so by that we mean that the power in, or the power absorbed, is equal to the power emitted. That's the power emitted back to space as thermal radiation. Okay? If that weren't true, if there were more power in than power out, then the Earth would keep heating up. If there were more power out than power in, then the Earth would keep cooling down. Okay? So on average, we know over millions of years that the temperature might vary day to day, it might vary place to place, but on average, the temperature of the Earth has not changed so dramatically. So on average, the Earth is in equilibrium. Okay? So we can find what that temperature, radiation temperature, is by setting the power in is equal to the power out. Okay? So that just means the power absorbed is 236 watts per meter squared. So that's this left-hand side over here, and that has to equal to the Stefan-Boltzmann constant times the temperature of the Earth to the fourth power, so the average temperature of the Earth to the fourth power. When we set those equal, we can solve, this is just a constant, so we can get rid of that, and we can solve for this temperature. Okay? And when we solve that, this model predicts that if the Earth did not have any atmosphere, that the temperature, the average temperature of the Earth, would be about 255 Kelvin, which in human units is minus 18 degrees Celsius or 0 degrees Fahrenheit. Okay? So that is the extreme case. This is what the temperature of the Earth on average would be if the Earth did not have an atmosphere. Okay? And it's a very simple model, and it's a pretty clear prediction. This is the low end. Of course, we know that the temperature of the Earth on average is warmer than this. Okay? Life wouldn't be able to survive in such cold temperatures. Okay? And that comes from the effects of the atmosphere. Okay? So in reality, what we measure the average temperature of the Earth is about 288 degrees Kelvin, which is about 15 degrees Celsius, or about 59 degrees Fahrenheit. So 59, 60 degrees Fahrenheit, that's about the average temperature of the Earth when you integrate over the whole surface area. Okay? And that increase over what this model predicts without an atmosphere is due to the effects of the atmosphere absorbing the infrared radiation that is emitted from the Earth. Okay? The atmosphere heats up and heats back up the Earth. Okay? So this is that increase is due to natural greenhouse gases in the atmosphere. Okay, and those are largely water and some carbon dioxide. Oh, let me put that up. Okay, we, of course, are increasing the carbon dioxide concentration quite a bit through our using fossil fuels, but there is a natural amount of carbon dioxide that comes from natural processes, primarily from plant respiration and stuff. So these are perfectly natural, they're in the atmosphere, and these are what keeps the temperature here about 33 degrees Celsius higher than it would be if the Earth didn't have an atmosphere at all. Yeah. So that is, of course, that's what makes life possible. Okay, so the reason that the temperature is warmer on the surface of the Earth, like I've said, it's because the atmosphere does exist. Okay, there is an atmosphere on the Earth. It is not transparent to infrared radiation. It does absorb infrared radiation. Okay, and the amount of infrared radiation it absorbs coming up from the Earth will determine the temperature of the atmosphere. Okay, and the hotter the temperature of the atmosphere, the hotter the temperature of the Earth. So let's look at a second model, which is the opposite extreme, which is the case if we do have an atmosphere, but that atmosphere is completely opaque to infrared radiation, which means that when the Earth emits its infrared radiation back towards space, the atmosphere is in the way and it's going to block it. It's going to absorb it completely. Okay, so that is our extreme case number 2. You can think of this as the maximum greenhouse effect. And this will tell us what the limits are of the greenhouse effect, or the other way to think about that is, what is the worst effect we could have on the Earth's temperature if we keep increasing the amount of greenhouse gases in the atmosphere? So in this case, the atmosphere is still transparent to visible. So it's still transparent to sunlight, which is visible, but it is opaque to infrared. IR, by the way, means infrared. I'm getting lazy. It's invisible, it's opaque to infrared, which means that it completely absorbs it. Okay, so let's draw the picture of what the atmosphere would look like in that case. Let's see, this is a very expensive camera, but it's kind of in my way. So let me see if I can spend 10 seconds and get this out of here. There we go. Okay, so now let's draw this model again, but this time we're going to include the atmosphere in here, and we're going to make it opaque to infrared radiation. So there is a sun again. Our sun is shining down. Here's the Earth. Okay. The only difference in this second model is now that we're going to have an atmosphere up here. It's going to be extreme atmosphere. So, completely opaque to infrared radiation. So once again, we've got 342 watts per square meter of sunlight that's coming in. Okay. Let's assume for now that the same amount is reflected back. 106 watts per square meter reflected off the surface. So once again, that is the 31% albedo of the Earth. Okay. So that means we still have 236 watts per square meter, or about 2/3 of the sunlight that's being absorbed into the Earth. So that's heating it up. Okay. And now the Earth is radiating back thermal radiation. Okay. So, but the difference is that that thermal radiation is getting absorbed in the atmosphere. So that means the atmosphere is heating up. Okay? And as the atmosphere heats up, it's going to provide some heating back to the Earth. Okay, so if we're doing this full equations, that just means there would be a couple more steps we'd have to add. How much the atmosphere is heating back up, how much the radiation of the atmosphere is going back to the Earth. Okay? But let me just tell you what the effect of this is. Okay? The effect of that is that there is a maximum temperature that the Earth would reach because of this effect. And it is very easy to calculate. So the maximum limit on how much the Earth heats up and this is over the case with no atmosphere. So we calculated the case with no atmosphere. We saw that with no atmosphere that the average temperature was about 255, or would be 255. Okay? This model, when we factor that in, gives us a factor over that which is just 2 to the 1/4 power. Extremely simple prediction. Okay? That just comes from these temperatures, the radiation going as the temperature to the 4th power. So that's where, when we're inverting the equations, we get this factor of 1/4. Okay? So, but a factor of 2 to the 1/4 power is equal to about 1.2 in temperature. Okay, so that just tells us that with this extreme atmosphere, where all the infrared absorption from the Earth gets absorbed in the atmosphere and does the maximum amount of heating, we would have a factor of 1.2, or a 20% increase in temperature over the case where there was no atmosphere whatsoever. Okay, so let's put some of these numbers into a table. Okay, so we've got the cases, no atmosphere. That was the first model we looked at. The current value of these temperatures for the Earth and then we've got the model we just looked at, which was the maximum greenhouse effect. Okay, so those numbers that we found were that with no atmosphere, the average temperature of the Earth would be about 255 K. So that compares with our current value, which is 288 K. Okay. And then we saw for the maximum greenhouse effect, so if we did our worst to the atmosphere, we added all the CO2 and methane and water vapor, everything we could throw up there to increase the temperature. The maximum temperature would be 20% higher than this case, which turns out to be 303 Kelvin. Okay, so since most people don't think in Kelvin, let's put these numbers in human units. So that's minus 18 degrees Celsius. The current value is about 15 degrees Celsius. And the maximum would be about 30 degrees Celsius. Okay. And in Fahrenheit, that would be about 0 degrees Fahrenheit, so very cold. The current temperature is about 59 degrees Fahrenheit on average over the surface of the Earth. And the maximum, if we really pumped up the greenhouse effect, would be about 86 degrees Fahrenheit. So this is the maximum limit on how much effect that we can have on the atmosphere. Okay, so it's about, what is that, 27 degrees above where we are now. So now when we're talking about the greenhouse effect in terms of carbon dioxide in the atmosphere, methane in the atmosphere, or the amount of global warming you've seen over the last century, we're still in the single digits here, so a few degrees. But even a few degrees can have a very big effect, potentially on the Earth's climate. So, but it could be a lot worse. We could be getting a lot worse, okay, if we kept on going. So let me just make a couple points, and then we've got some slides I want to show you. So about the greenhouse effect and gases. So of course you can see from these temperatures that over the case with no atmosphere, no greenhouse gases, and the case that we currently see, that the greenhouse gases in the atmosphere already play a very large effect in heating up the surface of the Earth. Okay? So this isn't really a mystery. Okay? There's some people who debate whether the greenhouse effect actually happens or not. It happens every day. Okay? There is a greenhouse effect. The predictions of it are what happens when we put more infrared absorbing gases in the atmosphere is not a mystery. Okay? It's very, very basic physics. Okay? And it's already what's responsible for warming the Earth over the case when we have no atmosphere. 1 second. Okay? So yeah, this is very basic physics. There's no real dispute on that. Okay? And in terms of the greenhouse gases, there are 3 that are important. Let's see, did you have a question here? Uh-huh.
Why won't it keep heating up if like the Earth cannot get heat out through thermal radiation?
Right, so in this case, so the question is, why doesn't it just, in this case for the extreme case, why doesn't the Earth keep on heating up even higher and higher and higher? Why is there a limit? Okay? And the reason is because the atmosphere, if you look at this very carefully, when the atmosphere heats up, the atmosphere emits radiation as well. As it gets hotter, it's got a temperature, and that temperature will emit as well. So the limit in this case is basically, I didn't go into this in too much detail, but if you want to think about it, it's a good thing to think about. The limit is when the Earth is cooling, not because the Earth is radiating to space, but because the top of the atmosphere is radiating to space. So the atmosphere is cooling. That's where the power is leaving the surface of the Earth. Okay? In order for that to happen, the atmosphere is heated up, and then that affects the surface on the Earth by this factor of 2 to the 1/4 power. So if you want to play around with equations, I'd be happy to do that during office hours. But it's pretty easy to show once you realize that once the atmosphere starts heating up, it's going to be radiating power to space. Yeah, actually, are there any other questions about these models before we talk about the greenhouse gases? in a little bit more detail? No? Okay, so let's talk about the gases, and then you guys can have some more questions if you want. So, greenhouse gases. There are 3 of them I want to talk about. Let's see, let's go over to this board. So when we use the term greenhouse gas, basically what we mean by that are any gases in the atmosphere that naturally absorb infrared radiation. So normal air is actually pretty transparent to infrared radiation. So it's only trace gases in the atmosphere which occur naturally, or some of them are man-made, which will absorb the infrared radiation. So okay, there's more than these 3, but these are sort of the 3 dominant ones that are that have the major effects. And then there's other ones which are a little bit smaller. So the first one is water. Okay, water is the largest component. And of course, it is mostly natural. So water alone is responsible for most of this difference between the temperature, what the Earth would be without an atmosphere, and what it currently is today, so about 33 degrees Celsius. The reason we don't usually talk about water when we're talking about global warming is because water is very well self-regulated in the atmosphere. So it's self-regulated on very short time scales. And on short time scales, we're talking about on the order of 10 days. And by self-regulated, we're talking about rain. If we get too much water vapor in the atmosphere, well, Mother Nature knows how to deal with that. It rains, right? So, and it rains on very short time scale. So we could have, you know, a major catastrophe, some underwater volcano goes off and pumps up a huge amount of water vapor into the atmosphere. And we wouldn't worry about that causing global warming because we know that, you know, in a couple weeks, all that water would be gone. It would come down as rain. So it would be very naturally regulated out of the atmosphere. Okay? So water is mostly natural. It's largely natural, and it's very well regulated. Okay? But we can't ignore it for when we're talking about global warming because it complicates the other gases in ways that we'll come back and talk to about in a few minutes. Okay? It has several feedback mechanisms, and a lot of the uncertainties about global warming actually come from the uncertainties of how water vapor acts, okay, in the atmosphere. So we'll come back to that one in a second. The second one is the one that usually dominates discussions of global warming, and that's carbon dioxide. So it does occur naturally. And it has played a large part in warming the Earth's atmosphere and its surface up to the temperatures that the normal temperatures we see today. But it has increased quite dramatically from 275 roughly parts per million. So ppm means parts per million. So this is just the very small fraction of the atmosphere that is composed of carbon dioxide gas, 275 parts per million, to the current value, which is about 375 parts per million. So that's a 36% increase in the last century. Okay, so, and of course that is believed to be in large part dominated by the burning of fossil fuels, that increase. Okay, which produces carbon dioxide, which is emitted in the atmosphere. By the way, burning fossil fuels actually emits twice as much water as it does carbon dioxide. Okay, so which is actually a stronger absorber of infrared radiation. Okay, but that doesn't have any long-term effects, okay, because the water will come out of the atmosphere within a few weeks. Okay, carbon dioxide, the main problem with that is that it's not naturally regulated. In the atmosphere, especially in the upper atmosphere. There are no natural processes that get this out of the upper parts of the atmosphere. Right? So that means that it has a very long time that it stays in the atmosphere. Okay, it will naturally stay in the atmosphere for 100 years or longer. Okay? There's a lot of work being done to figure out how long it can stay, but we know it can stay in the atmosphere for a very long time. So all that carbon dioxide we're putting in the atmosphere today is going to be there 100 years from now. Okay? There's no natural way for it to leave the atmosphere. Okay? Whereas any water vapor we're putting in will be gone in a couple weeks, so it's not such a big concern. Okay, and the last one that I want to mention is actually potentially even a stronger component than carbon dioxide. And it's definitely one we need to keep our eyes out for in the coming few decades. Okay, the third one is methane. Okay, so methane has also increased over the last century from about 750 parts per billion, so ppb is parts per billion, so it's much lower concentration than carbon dioxide, but it actually absorbs infrared radiation really strongly, so even though it's a much lower concentration, it can have a potentially bigger effect. It's increased from 750 parts per billion to about 1,750 parts per billion. So that's a 130% increase in the last century. Methane comes from a number of sources. So it does partly come from the production of fossil fuels. So not the burning, but the production of fossil fuels, the processing of fossil fuels produces methane. But it also comes from a lot of farming, so especially livestock and rice farming produces a lot of methane. And landfills, when we put garbage in our landfills and it starts decaying, it produces a lot of methane that goes into the atmosphere. By comparison with carbon dioxide, methane actually does get regulated. It's naturally regulated in the atmosphere. On about 10-year timescales. Okay. So that means if we did suddenly, find a way to decrease our methane production and contamination of the atmosphere, then in a couple decades, the effects of it would go away and it would reverse fairly quickly. Okay? But before that happens, it actually is a potentially stronger absorber of infrared radiation than carbon dioxide. So this has the effect that it can potentially produce more warming than CO2. carbon dioxide. Okay, but it's naturally regulated on shorter time scale. So it has the potential of being a bigger effect on the atmosphere in terms of temperature increase, but in some ways it's less of a worry because we know that if we did stop producing all that extra methane that it would go away in a decade or a couple decades. Okay, so let's see. I've got some slides I wanted to show on the greenhouse effect. Let's see, can we switch over to the projector? Okay, I'm going to post these slides on BSpace, and there's a lot more slides in here than we're going to go through today. So, oh, there's nothing over there. It is. Let's see, where are we on the right port for this? Let me see, maybe I need to detect my display. Let's try. You want me to swap to the other input, maybe? Let's try it. System is currently in operator mode. Okay, let's see. So I'm on VGA2 way, which is stage right. Ah, perfect. Okay, thanks. Okay, so this is a plot of some of the greenhouse gas concentrations over the time on this is might be pretty amazing if you haven't seen this before. This is 600,000 years before the present. So this is 600,000 years ago going up to the current day. Okay? These greenhouse gas concentrations are measured by ice core samples in Antarctica. So Antarctica, the ice in Antarctica is kind of like tree rings on a tree. So every year there's another layer that's added, okay? And it makes little ice layers that are very clear to distinguish. Okay? And those ice layers trap little air bubbles in them. And so when we drill down on ice cores, it's literally like counting tree rings. We can go back in time the deeper we drill, and there's all these little bubbles trapped in there, and all those little bubbles trap basically sampling the atmosphere from that time, okay, when that ice was formed. And they've been able to go back almost 700,000 years there. The red curve here is the carbon dioxide concentration, and this is the scale on the left-hand side. This is a little bit of a confusing plot, but this scale goes with the red curve. This is the carbon dioxide concentration. And you can see over time that it has varied between about 200 parts per million to about 280 parts per million. Okay, so there is a natural variation of the carbon dioxide. These gray bands are, I believe these are known ice ages, and you can see there is a correlation between carbon dioxide concentrations and those. Actually, those were probably warming periods, not ice ages, because of the way those are matched. But what you really want to look at is over here on the right-hand side, where this is the concentration just in the last century, and you can see how much it has jumped up quite measurably over all the previous concentrations for hundreds of thousands of years on the Earth. Okay. The next curve down, the blue one, is the methane concentration, which we talked about as the third gas, and you can see, and its scale is over here on the right-hand side. So you can also see how its concentration has varied, but not by a very large amount until the last century when it's jumped up quite dramatically by 130%. This is a blow-up of those curves just over the last, this is 10,000 years on this scale, so there's carbon dioxide. And then the little inset here is a blow-up over the last 200 years. And so the measured carbon dioxide concentration has gone up quite dramatically, 36%. The methane has gone up even more dramatically, 130% over the last 200 years. And nitrous oxide, I'm not going to talk about today, but it's another effect. That's the same plot, just so you can see the data. The temperatures. So there is a lot of debate, and unfortunately not among scientists, but mostly among politicians, about the global temperature measurements. And there are skeptics about how these are actually performed, but the measurements are actually pretty clear at this point. This is not the latest data. This is from 2007, but this is just the trend of the average temperature. So the way this is found, you might think, well, the temperature varies quite dramatically everywhere on the Earth. So this is the average. They find the average at each location, and then they find the deviation from that. Okay? And so this is really how much the temperature has varied over what it was on average from that location. And you can see there is a lot of scatter here. So this is going back to 1850. But the trend is pretty clear, and so the current best estimate is that over the last century, the temperature went up by just about 1 degree Celsius over the surface of the Earth. There's a lot of scatter, and that might vary from location to location, so there are a lot of people that will be critical of this data. But I'd say that it's a very clear trend. So there are people that still doubt this. But the next one is one that you cannot really doubt, which is the sea level. We've been measuring sea levels quite regularly. I think it's very important for shipping and stuff like that. And over the last century, the sea level has gone up. This is in millimeters on the left-hand side. This overall trend in the last century is about 20 centimeters. So the sea levels have risen by 20 centimeters over the last century, which is very clear and easy to measure. This last one is the snow cover, which is a little bit harder to measure, but this is trying to show that snow cover has decreased, which is supposed to be a measure of the overall temperature increase. It's bad for snowboarding. Okay. This is a plot of the temperature measurements at different locations. So each one of these curves on here, you guys can look at this more closely when it's posted online, but each one of these curves is a measurement of the temperature. This is the date on this axis, and it's a temperature at these different locations around the surface of the Earth. And see, there are a lot of variations, but the big question is, what are the trends? And the trends are pretty clear everywhere globally over the last century, that this has been increasing over the last 100 years. This is a plot of just averaged over the continents. So the black lines are the average measurements for each one of these different continents. The red curves here are sort of the range of predictions from models. So the modeling is very difficult to do for this. And so if you look at any two models, they're not going to agree with each other exactly. But the idea is that they can take lots of models and see what the trends are in the models, just like the trends are in the data. So the red curves are the trends in the models based on human inputs, so increasing the greenhouse gases in the atmosphere. And the blue are what the models would say if the if humans were having no effect on the atmosphere. So you can take that for what you will, but it's actually a pretty good confirmation on the models that they're doing a pretty good job of predicting this. Let's see. This is a very complicated plot. And so if it hurts your brain, don't look at it too closely. But this is a plot of absorption. So this is how much the atmosphere absorbs, or how much these gases absorb radiation versus wavelength. Okay? So remember that the Earth emits in thermal radiation around 10 microns, so that's in this range right here. Okay? And you can see water, so this big hump here is showing that water absorbs a lot of radiation down here and a lot of radiation up here. Okay? That actually kind of straddles the peak of where the Earth is radiating. Okay? But you can see that CO2 has this big absorption band right here that overlaps with that. So while water is the dominant greenhouse gas in the atmosphere, naturally CO2 complements it, unfortunately, really well in terms of absorbing the infrared radiation. So that's why CO2 has such a big effect. The more that increases, the more that parts of the infrared band that water doesn't absorb will get absorbed into the atmosphere. And let's see, the only other things I wanted to show here, these are mostly for you guys to look at online. This is a prediction, which is really difficult, of what the temperatures on the Earth will look like and the rain will look like over, I think this was meant to be towards the end of this century if we keep on with the current use of fossil fuels. And so this is not a single model. This is sort of the average of many hundreds of different scientific models sort of put together and trying to see what the trends are, which suggests that there are areas that get warmer and there are areas that get cooler because of the complicated circulation patterns. But overall, you can see a lot of the populated areas are getting much warmer. A lot of rainfall over northern Europe, a lot of more deserts in northern Africa and perhaps even southern Europe. Okay. And this is a plot of predicted rainfall. Once again, this is not a single model. This is many hundreds of models. And blue means areas that will get more rainfall, and red means areas that are predicted to get less. Okay. So I'm going to post these online, and we can actually even have a discussion on the forums about these if you guys want. But I wanted to separate out some things which are, I think, pretty undisputable facts about global warming and greenhouse gases versus some things which are a lot more speculation. So let's see, wait, can we come back to the board? Okay, so in terms of facts, okay, so the first one, which I'd say is indisputable, is that carbon dioxide, CO2, and methane have increased dramatically over the last century in the atmosphere. There have been a lot of measurements of this, so this is pretty indisputable. Okay. Related to this is that the basic mechanism of the greenhouse effect is so extraordinarily simple that there is no question that increasing these is increasing the temperature of the Earth. There are complications, which I will discuss in a second, but there is no doubt that these are warming the Earth. This is just such basic physics that these are warming the Earth, that I don't think that is disputable. So the second thing which I would say is a fact, which does not mean that it is absolutely pinned down, is that the global average temperature has increased over the last century. Okay. You can debate by how much you scrutinize the data and the methods that different scientists are using, exactly how much, but I would say overall the trends are irrefutable that this has been about 1 degree Celsius. Right? Might be 0.7 degrees Celsius, it might be 0.8 degrees Celsius. The details of that, of course, are important. It is important in the details, but in the big picture, the fact that we know that it has increased over the last century is probably the most important thing to take out of that. So I'd say that is a definite fact. Sea level has risen. Extremely well measured, very small error bars, okay? And it has risen by about 20 centimeters over the last century. By the way, if you're going to buy property, I would not invest in Alameda. Its prospects are not looking very good going forward. So, and I would say there is pretty good evidence that snow cover has decreased. The error bars on this are still pretty large, so there must be some systematic, there are some systematic errors in that, but it appears to be about 10%, so maybe it's 12%, maybe it's 8%, but I think that it's pretty incontrovertible at this point that snow cover has decreased, which is of course believed to be due to warmer temperatures. Okay, so when people are discussing the greenhouse effects and global warming, there are a lot of times where these facts get confused with remaining uncertainties. So I want to let you guys know what are the major uncertainties in terms of the greenhouse effect, okay, and global warming, and maybe how they relate some to these other ones. So the biggest one is the effect of water in all of this. So water, of course, is natural greenhouse gas. It's the dominant greenhouse gas in terms of warming the Earth's atmosphere. But water can have a positive or negative feedback. And this is, whether this is going to be a positive or negative feedback, kind of is selectively chosen by your political intentions, I would say. So, water, what I mean by positive feedback. So positive feedback means that as the Earth warms up, that the water vapor will keep it increasing temperature so that it doesn't actually limit the amount that it heats up. So negative feedback means as the Earth heats up, the water somehow will affect the temperatures and try to drive them back down. So that's a negative feedback effect. So there are several ways that will happen. But let me point out that when I say that, I think I erased it, that this is a fact, that CO2 and methane in the atmosphere are definitely warming. That is an irrefutable fact. Some people will or there is a question of whether the water will actually increase or decrease the warming of those other gases. And the idea is this. It's pretty simple. So, as the Earth warms up, okay, you can imagine that we'll get more ice melting, like at the poles. There'll be more rainfall because of that. Okay? The sea levels are higher, there's more water around, and there might be more clouds because there's more rainfall, because all the ice caps have melted. Well, so clouds would have a negative feedback. Okay? And the reason is that if there's more clouds, then more sunlight will get reflected before it gets to the surface of the Earth. So more clouds could increase the albedo. Remember, we were talking about in our models, the albedo, the fraction of the sunlight that gets reflected. And if the albedo increases, then there's less solar radiation that's absorbed on the surface of the Earth, which means that it would have a cooling effect if there are more clouds, more cloud cover. That is only one effect that water can have. It actually has some positive effects, positive feedback effects as well. First off is what I said, less ice. If there's less ice and less snow cover, then we're replacing land that's covered by white, which is very reflective of visible light, with stuff that's covered by brown or green, which is very absorptive of light. And so that has the opposite effect. So the less ice and snow means that there's less reflection, which means that the albedo is decreased. Okay, so that actually means more warming. So the other effect is that if there's more, if the atmosphere heats up, warmer air can hold more water vapor. And if it's got more water in the air to start with, then the effects of the water vapor on the greenhouse effect is going to be even stronger. So water is a big uncertainty in the models of global warming, or in the predictions of global warming, because it could either make it stronger or it could make it weaker. And the details of the processes that are going on are so complicated that they're very hard to measure. They're very hard to predict. Okay? But that doesn't mean they're impossible. And a lot of people are working on these. This is probably the dominant thing that a lot of the global climate modelers are working on, is the effects of water vapor on this, and whether it be positive or negative. And right now, it does not look good. And people claim this was because of the bias of the scientists, but right now it looks like that these effects on, less reflective ground cover, so more earth and more green and less ice and snow to reflect the light, and the increased water vapor in the atmosphere would have a net warming effect over a net decreasing effect. Okay, so the fact that the water vapor, though, is still a little bit uncertain does not counter the effect that carbon dioxide and methane are warming the atmosphere. Okay, this is a given. This is either going to make it a little bit warmer or a little less warm, depending on the details of the Earth's climate and the water feedback. Okay? But that's not negating the fact that the other gases are actually warming it up. And right now, this looks like it's actually going to be a positive feedback. So the warmer the Earth gets, the water vapor is sort of on the scale of doubling the effect of the heating of these other gases. So, but I'd say that is still a major uncertainty. Okay? The other ones, I won't go into as much detail, but the effects of increased temperature on climate and weather, I would say, are very uncertain. So just because the Earth's heating up doesn't necessarily mean we can predict what the climate's going to look like or what the weather's going to look like at any position on the Earth. So that is extremely uncertain. A lot of the weather on the Earth is dominated by things like the ocean currents, okay, which will definitely get affected by increased temperatures, but those are very complicated systems. So we can almost guarantee that things will change, but exactly how they will change is, I think, extremely uncertain. So the ultimate amount of temperature change, how much the Earth could heat up, is still largely uncertain, and that's because of this effect of the water. There's still a major uncertainty of whether this is going to be helping, is this going to be heating up more or less if we put the greenhouse gases in the atmosphere. And then, of course, the economic effects of global warming, I think, are extremely uncertain. So this, unfortunately, is going to be a major issue dominating your lifetimes. So I think that it's good to differentiate these. Okay? What are the facts that are basically irrefutable at this point, and separate those out from what are uncertainties. Okay? And there still are a lot of uncertainties, okay? But that doesn't negate the fact that the basic underlying physics of global warming is so simple and trivial that there's no doubt that it's actually going on when we're pumping more greenhouse gases into the atmosphere. Okay, let's see. Are there any questions on this? Okay. I know you guys probably have a lot of exposure to this at this point, so yeah. Hmm?
After about tipping points where the climate will just change and we can't go back, what's the most plausible tipping point that would happen?
So the question is that there's been discussion of tipping points. So the idea is that the Earth gets to some point and then there's no going back. Is that the idea? Well, I would say historically we've seen a lot of tipping points, and that's actually part of your essay question for this week. So on the ice ages, we've seen where the global climate has changed dramatically in the past between going hotter and colder. As far as going future and how hot we can get, we've seen a limit here in terms of what's the absolute worst that we can do. We are nowhere near that, but I don't think we want to get anywhere near that either. So, okay. Any more questions? Okay, we're picking up on waves next lecture.